Hello, everyone. Hope you are having a great weekend. And as I promised, I'll be recording this video um, with some practice problems. And hopefully, this will find all of you safe and um, well prepared for the next exam, I would say. And of course, if you have any question after watching this video, don't hesitate to send me an email, okay? All right, so I'll start with this problem. What happens when you have a fraction like this? Let's say your y is a fraction, okay? Anything, let's say a 5, and then a function of x, okay? Then what happens? Let's see one example of it, okay? Let's say we have 2x minus 3, just an example, okay? 2x minus 3 in the denominator, and of course in the numerator we have 5. If I say, what is the derivative of this? What should you do? And if you have a problem like this, you just need to rewrite that first. So we can actually write it as 5 times 2x minus 3 to the power 1. Do you agree? And this is because 1 over x can be rewritten as x to the negative 1. It's actually true for any exponent. This can be written as x to the negative 2, so on and so forth. We can write 1 over x to the n as x to the negative n. Okay, I'm using the same principle here to rewrite the denominator as this. Okay, and now if I find the derivative of 5 times 2x minus 3, the quantity inverse, you can imagine I can keep the constant outside using the constant function law, and for the derivative of this, the exponent will come in front and we'll have 1 less in the power, so it's negative 1, negative 1. Remember, the formula was n x to the n minus 1, right? And now using the chain rule, since this is not exactly x, is it? It's not exactly x, it's something else. So we need to use the chain rule, and using the chain rule, we can find the derivative of 2x minus 3. Now let's carry on doing that. So it will be negative, I should write a negative 5 because I can factor out that negative 1 outside. It will give me negative 5. This will be 2x minus 3, the quantity to the power negative 2. And what's the derivative of 2x minus 3? The derivative of 2x is going to be 2, right? And the derivative of 3 is 0 because it's a constant, right? The derivative of 3 is 0. So if you have a problem like this, your final answer would look like this: negative 5 times 2, negative 10, and 2x minus 3, the quantity to the power 2. That's your answer. Or you might rewrite it as this: negative 10 over 2x minus 3, the quantity squared. I'm just using the same principle here again. Right? So this will be your derivative if you have a fraction like this. All right? Okay, so this is a type of question I wanted to share. The second type of question be like this. What if you have, excuse me, what if you have a square root function? Let's say a square root of, let us use the same function, 2x minus 3. What if you have something like that? So obviously, you can rewrite it as 2x minus 3, the quantity to the power half, right? Because that square root is nothing but the second, or I mean, if I rewrite it, is the to the power half. It's the exponent half, right? For example, if you have anything like this, the nth root, you can actually rewrite it as x to the 1 over n. So that's the principle I have used here. So you can rewrite it like this and find the derivative afterwards using the power rule. So the power comes in front, 2x minus 3 half minus 1, right? Again, using the same formula, n x to the n minus 1. And of course, it's not exactly n. So again, we'll multiply the derivative of whatever we have in place of that x using the chain rule. Now let's carry on. We have half 2x minus 3, the quantity to the power. Half minus 1 is a negative half. And again, we know the derivative of 2x minus 3 is 2 from this one, right? So overall, you can see this half and 2 will get cancelled. And we can rewrite it as 1 over 2x minus 3 to the power half. Do you agree? Or maybe we can rewrite it as this, 1 over square root of 2x minus 3. Whichever you feel like writing, it's completely fine. Okay. This is one of the approaches, or you could actually use one of the straightforward formulas. If you have if you have square root of x, if you have y equals square root of x, the derivative is straight away 1 over 2 square root of x. You can straight away use this formula. Okay, this is one of the formula you can use. All right, let's use this particular formula in our previous problem and see if we get the same result. Okay, so first of all, our y was square root of 2x minus 3. So using this formula, we should get y prime equals to 1 over 2, whatever we have in place of this x, right? So 2x minus 3. But is this the isolated x like this? Not really. So we need to multiply the derivative of that. And we know the derivative of this part is 2. Let me rewrite it for you. So let's keep it like it was, 2x minus 3. And the derivative of this is 2. We know that. And again, if we cancel these two, we get 1 over square root of 2x minus 3. And this is exactly the same as this. So whichever you think would be convenient, you can just follow that. All right. Okay, so that's type 2. What's type 3? Let's see what is another type of problem you might be struggling to solve. Let's say I have a problem like this. Limit x tends to, let's say 5, and we have x minus 5 at the bottom. Okay, and 5x squared minus 125. Let's just assume that's the case. Okay. All right. Now, if you're trying to find limit for this, what should you do? What should we do rather? Now, we can actually start factoring out. So what can we factor out? Let's see. First of all, as I said, you can plug in the value in place of x if and only if your functional value, or rather whatever you have, this expression, I shouldn't say functional value, anyway, this expression is defined. It doesn't give you any undefined value. For example, if we plug in 5 here, we get 5 minus 5, that is 0 in the denominator, which we don't really want, because that would give us an undefined value. So if that's the case, we need to see if there is any way we can reduce it to a shorter format. If we can use any other techniques to get a defined value, okay? And a good way is to see if we can factorize it. Let's see if we can factorize this. I got some emails about this factorization. Hope this will help you. So first of all, the denominator is already done and dusted. You can't really reduce it anymore. But in the numerator, I can see I can factor out of 5 from both the terms. So if I factor out of 5 from the first term, I have 5, my bad, I have x squared, right? Because I'm just taking 5 out of that 5x squared. And from the second term, I can, if I can factor out a 5, I still have a 25 here. Do you agree? Because if I just multiply 5 times 25, I get 125. So I can factor out a 5. Obviously, you can only factor out a thing which is common in all the terms, right? So I can do this. Okay, now let's see if we can do any other modification to it which will simplify our life. So now let's keep the 5 outside. If I say I can actually use another formula on this, x squared minus 25. So you know that there is a formula, the difference of the squared, right? Which is this. So I can use this here because x squared minus 25 can be rewritten as x squared minus 5 squared. Do you agree? And then I can use this formula to write x plus 5 times x minus 5. I'm just using this particular formula, right? So if I do that, this would be x plus 5, x minus 5 over x minus 5. And again, we can cancel this out, and finally, we'll have limit x tends to 5 5 times x plus 5. Now if I plug in 5 in place of this x, this will give me a defined value. No worries with that. So I can plug in the value here, 5 plus 5, right? So it's 10. 5 times 10 is 50. So again, you can see, even though when we just eyeball, when we just had a view for the first time, this problem looked like that it will give us an undefined value, right? Because if I plug in 5 here, it would have been 0 in the denominator. But you can see you can actually modify this and get a defined value out of it. So this would be another type of problem you might be needing in the exam. Okay. All right. Let's see what else we couldn't show in the discussion, but we should know anyway. Okay, so let's try this one. Let's try. Okay, let's try this one. So if you have a function, let's say this is our problem 4. If you have a function like this, limit x tends to 0, oops, sorry. Limit x tends to 0. Sin x over x. We know we can straight away write 1 in place of it. That's true for limit x tends to 0 cosine x as well. Oh, sorry, I should write 1, not 0. Yeah. We can use this formula to simplify and get a very good result, very good limit from a function. Let's see how. Okay, so limit x tends to 0. Let's say I have sine 5x. Okay, let's have sine 5x over x. Okay, and I want to find the limiting value from it. What should you do? So I know that whenever I have the same coefficient here for x tends to 0, I'll get 1. So if I can somehow make it 5x, then the coefficients will be same. And I will be able to write 1 in place of that. Because you can clearly understand why. Let me briefly tell you why. If x tends to 0, don't you think 5x also tends to 0? If you multiply 5 times, that should still tend to 0, right? That means whenever x is approaching 0, 5x is always approaching 0 as well. Or whatever it is, it's 7x, 6x, whichever you multiply, it doesn't matter, as long as it's going in the same direction. So if for x tends to 0, sine x over x is 1, I can clearly understand it should give me any other function tends to 1 as well whenever the coefficients are same, like this, 5x over 5x, or whatever it is. So let me show you how to bring a 5 here, which we really want. We don't have a 5 to start with, right? But we want a 5 here. So let's do it this way. Let us write the required 5, I mean, which we want. So I have written a 5 in the denominator, right? but this equal sign holds me back because your value needs to be the same. You can't really write a 5 in the denominator out of nowhere. You need to keep the value intact. So if I have a 5 in the denominator, I need to have 5 in the numerator as well, so that whenever I can cancel this out, or in my imagination, if I cancel this, I still get the same function which I started with, right? So if you multiply the denominator by something, you need to have the same thing in the numerator as well, and vice versa. Okay, now we can keep this 5 outside because it's a constant. And again, we have sine 5x over 5x now. And as I said, since x tends to 0, 5x also tends to 0. Because if you're multiplying it and if it's going in the same direction, the value still should approach the same to the same point. So using this particular law, I can write this as 1. And this should give me a result, which is 5. And you can do this for any other problems like this. Whenever you have x tends to 0 and you have a sine or a cosine function, you can make these adjustments and find the limit. Okay. All right, so let's try the next one. Let's say we have y equals to sine x. Okay, I'm just giving you a short intro how to find the higher order derivatives. So if you have sine x, we know the derivative of sine x is cosine x, right? We know the formula, so you can write it straight away. But what if I say find the second derivative? Now what should we do? That means now we're going to find the derivative of this, whatever we have after the first derivative, right? And the derivative of cosine x is negative sine x. Do you agree? What if I say find the third derivative for me? That means now you want to find the derivative of the second one. Whatever you have after the second derivative, you are just trying to find the derivative of that. We can keep the negative outside, and the derivative of sine x is again cosine x. And you can actually keep doing it until it actually gives you a defined value. Okay. And of course, if you have any other laws or any other formulas to apply in between any of the steps, you have to do that. For example, in this case, we didn't really need the chain rule, but in some problems you might need the chain rule for finding higher order derivatives, right? And you have to use that. You might require to use the product rule. So whatever you need, or whatever you have to, you just keep an eye on that. Okay, just keep an eye on that, keep an eye on the problem, keep an eye on the expression, which law is required here, nothing else. So it's basically the same idea as finding the first derivative, but just make sure that for finding higher order derivatives might require more methods simultaneously. Okay. All right. What else? For the exam, I would like you to know that you need to use the implicit differentiation, the chain rule, and the product rule. Obviously, the product rule is one of the most important things. So you will actually need these 3 type of problems the most number of times. You'll face this the most number of times. Okay, so practice at least 4 to 5 problems, if not more, of course. If possible, practice at least 10 problems from the chain rule, at least 4 to 5 from the implicit rule. And I guess if you practice these two, you will see you are already using the product rule, so that should uh, help you in the cause. That should help the cause overall. Anyway, so let me show you uh, one more problem from the implicit differentiation, and I'll pick a problem which will uh, require you to use all these 3 methods in the same problem. So it will be an implicit function. You'll need to use the chain rule, and in between you will see you need to use the product rule as well. So let me show a problem like this, and hopefully it will be helpful. Okay, so let's try problem 6. And we can pick, let's say, y equals to natural log of e to the xy. Okay, let's see. I hope this will require all the 3 things we need to do. All right, let's use, okay, yeah. So now we're trying to find the derivative of a logarithmic function, right? So this dy dx on my left, and on my right, I'm trying to find the derivative of this. We know the derivative of the natural log is actually 1 over x, right? Natural log of x is 1 over x. So whatever we have here, we can copy that here. Do you agree? But it's not exactly that x, is it? It's not exactly that x, right? So we need to use the chain rule, and we need to multiply it by the derivative of e to the xy, right? Okay, let's keep doing that. 1 over e to the xy. And we know for e to the x, the derivative is always e to the x. We can actually keep it here, e to the x, right? But it's not, again, it's not exactly x, is it? It's not exactly x, right? So we need to find the derivative of x and y, x times y, and multiply that here. Do you agree? And again, this will get cancelled, and the derivative of x times y using the product rule, if I keep x, the derivative of y is dy dx. If I keep y, the derivative of x is, we know it's 1, right? But let's just write it here and then simplify. So x dy dx, sorry, x dy dx plus y times 1. So it's x dy dx plus 1. Are we done? And the answer is no, because we're looking for dy dx, and I have dy dx on both sides, right? So what should we do? We should actually isolate this dy dx, the terms with dy dx, right? So let's rewrite it first for your convenience. I have dy dx equals to x times dy dx plus y. So if I change sides for this, it will become dy dx minus x times dy dx equals to y, right? Or in other words, if you might say that I have subtracted x times dy dx from both sides, okay, whichever way you can remember it. I'm just trying to isolate the terms with dy dx, right? So now, as I'm trying to isolate it, I'll just factor it out. Okay, let's just factor it out. If I do that, I'll have 1 from the first term minus x from the second term. I'm just factoring it out, nothing else. Equals to y. And now, if I just divide both sides by 1 over x, or if I just change sides for that, it will become y over 1 over x. And this is your final answer. Okay? This is your final answer. I can actually use the logarithmic rule for that problem and simplify my life straight away. Let me show how. I know that for natural logarithm of x to the n, the exponent comes in front, right? So this can be written here, xy times natural log of e, and I know natural log of e is always 1. So instead, I can write xy times 1, which is xy. And now, if you find the derivative of y equals xy, you'll get the same result. Just use the product rule here, nothing else. And then isolate dy over dx, dy dx, okay? So these are the problems I wanted to show, which I couldn't show maybe. I've shown problems like this one, this 6, that's for sure. But especially for problems like 1, 2, 3, and 4, due to the shortage of time, I couldn't really show it. So hopefully this will help you to gain confidence on doing problems like this. And of course, if you have any questions after watching this video, just email me. And for the exam, again, if you practice problems like this, you'll be doing fine. And all you need to do is to find derivatives of different types of functions, nothing else. You'll be asked to find derivatives where you just need to use the formulas we have seen, the product rule, the quotient rule, how to find the higher order derivatives, derivatives of the trigonometric function, the inverse trigonometric function, the implicit differentiation. Just use the methods and you'll be there. It means my short suggestion would be to practice a couple of questions from each type. Okay. All right. So I'll see you tomorrow and let's talk more about the exam then. Bye-bye.